Welcome back. In this session, we will continue with the discussion on DTF, discrete time Fourier transform. Now, before we, and today's topic is sampling of this discrete time Fourier transform. Now, before we sample this discrete time Fourier transform, let's suppose our x of n is the sequence, and this sequence is now causal. Means we'll assume that the negative side of the sequence is 0, means the sequence is like this: x of 0, x of 1, x of 2, and so on. And suppose this is n point sequence now. So this is n point sequence now. Now we know that the DTFT of this sequence is given by, so the discrete time Fourier transform of x of n is given by x of omega is equal to summation n running from minus into infinity x of n e raised to power minus j omega n. And since we have assumed that the sequence starts from n equal to 0, so this will be equal to 0 to n minus 1 x of n e raised to power j omega n. So this discrete time Fourier transform equation is this. Now we know that the x of omega has a period of 2 pi, so is 2 pi periodic. And second thing we know about this is that x of omega is continuous function of omega. Now what do we mean by this? It simply means that the discrete time Fourier transform x of omega is a continuous function of omega. And suppose this is the discrete time Fourier transform of this x of n, right? So this is our discrete time Fourier transform. Now what we'll do, we'll sample this. So this cannot be stored in a computer, means computer cannot store. Actually, if this is a continuous function of this omega, we need an infinite values to store the discrete time Fourier transform actually in computer. So what we will do, we will sample this. So we'll sample this at regular values of omega. And suppose we take n samples of that omega between 0 to 2 pi. So suppose between 0 to 2 pi, we know this is periodic. We'll take how many samples? N samples of capital N samples of x of omega, and we'll take that samples at regular intervals of this omega. So suppose we sample it like this. Suppose we sample it like this. So 2 pi by n k, and k is the point where we sample. And suppose we sample it like this: k is 1, so it will be 2 pi by n, then k is 2, so this will be 2 pi by n times 2, when k is 3, and k is 4, k is 5, so on. So this is our n minus 1th sample by 2 pi multiplied divided by n, and finally this will be last by n into n divided by n. So we will simply write it 2 pi by n. So this will be 2 pi by 2 pi. So this will be 2 pi. It will be 2 pi n divided by n. So this is the nth sample. So this is our last sample actually here, n minus 1th sample of this. So how we are sampling this, please pay attention. So we sample this omega and we write it omega k 2 pi by n k, where k is varying from 0, 1, 2, so on up to n minus 1. So these are n samples of this omega. starting from 0, and we are taking this in the interval from 0 to 2 pi. So we sample this x of omega between 0 to 2 pi, and we take n samples of this. So what will happen to discrete time Fourier transform? So let's go to the expression now. We know x of omega is summation n running from 0 to n minus 1 x of n e raised power minus j, sorry, not 2 pi, this is omega n. So this is our expression. Now we are sampling omega, means put omega equal to 2 pi by n k. So what will happen to this? So x of omega will become, when omega is equal to 2 pi by n k, will become x of 2 pi by n k is equal to summation n running from 0 to n minus 1 x of n e to the power of minus, what is omega equal to? 2 pi by n k n. Now, so our expression x of 2 pi by n k is equal to summation n running from 0 to n minus 1 x of n e to the power of minus j 2 pi by n k n, where k is, let me write it like this, k is 0, 1, 2, so on up to n minus 1. Now, have a look at this. 2 pi by n will be constant because this will be n samples. So 2 pi by n will be constant. So as k changes, as k becomes 0, this will be x of 0. As k equal to 1, this will be x of 2 pi by n k. So at k equal to 2. So it's actually k that changes the frequency. See, omega k is 2 pi by n k. As k changes, omega k changes. So the frequency is determined by k. So the frequency is determined by k here. So the frequency is determined. So we write it as x of k. So we'll write it as x of k, and x of k is simply x of 2 pi by n k, which is equal to summation n running from 0 to n minus 1 x of n e to the power of j 2 pi by n k n. And sometimes it is written like this, sometimes you'll see this expression is written like this. Don't worry about it. Wn to the power of my again. So this is kn, where wn is equal to e to the power of j 2 pi, where this is equal to this, and this is referred as twiddle factor. Now, so our expression becomes our sampled expression of discrete time Fourier transform becomes x of k n is equal to 0 to n minus 1 x of n e to the power of minus j 2 pi by n k n. So this is our expression of the discrete time Fourier transform, and this is the sampled version of that. So this is the sampled version of that, and this is referred as discrete Fourier transform, and this is simply referred as discrete Fourier transform, or in short DFT, discrete Fourier transform. Why is it called a discrete Fourier transform? Since the frequencies are obtained by evaluating DFT, means by evaluating x of omega at n equally spaced points. Why is it called a DFT? I'm answering that. Why is it called n equally? Since the frequencies are obtained by evaluating DTFT, sorry, by evaluating DTFT, that is x of omega at n equally spaced discrete frequencies. Discrete frequencies. That's why the above relationship, means this relationship, is termed as discrete Fourier transform of x of omega. That's why x of k is referred as discrete Fourier transform. Why? Because since the frequencies are obtained by evaluating the dtft x of omega at n equally spaced discrete frequencies, the above relationship formula means x of k is called the discrete Fourier transform of x of n. And x of k, remember, what's the relationship between x of k and x of omega? X of k is the discrete version of x of omega. What's x of omega? dtft. X of k is the discrete version of x of omega. That's why this is referred as discrete Fourier transform, or simply the discrete Fourier transform. All right. I hope you understood. This is very, very important. This is what actually computer uses. Computer does not use the other three Fourier transform. I gave you already the four Fourier transform. If you remember, I already gave you the four Fourier transforms. If you remember that, what are the four? Let me show you those four Fourier transforms. Let me share that with you. See, this is the Fourier series that is the continuous. I hope you are able to see this. You can check it again. Or this is visible. Right. So this is the Fourier series, and this is the continuous and periodic series. And this is the Fourier transform. Computer cannot store it. And this is the discrete Fourier transform that we studied in the previous session. This is the discrete Fourier transform. Please check the frequencies. He's using a different frequency that we have used up to this for notation purpose. And this is the discrete Fourier series, and this is actually the same as DFT. This is the DFT that we have. So this is the DFT I'm talking about. All right. So this is, and this is actually, that's why I told you I will not assign these limits of that summation. If you remember, I didn't use this limits of the summation. If you remember, so this is our discrete Fourier series, and computer can only store this, not the other thing. And this is also referred as the discrete Fourier transform. So computer can only store this. So in short, remember this: the discrete Fourier transform expression is x of k summation n running from 0 to n minus 1 x of n e to the power of j pi to n k n. And this is the discrete Fourier transform. So this is DFT. Now the inverse inverse discrete Fourier transform means if we want to evaluate x of n, that means this will be given at that time. So x of n will be simply 1 by n summation k running from 0 to n minus 1 x of k e to the power of j 2 pi by n, but this will be plus now, n k. And here k is running from 0, 1, 2, so on up to n minus 1. And here n will be equal to 0, 1, 2, n minus 1. And these are the expressions of discrete Fourier transform and inverse discrete Fourier transform. This is very, very important. So this is our IDFT. Inverse discrete Fourier transform. So this is discrete Fourier transform, and this is the inverse discrete Fourier transform. This is very, very important. Very, very important. And this is actually what computer uses. Now remember, if you go to the MATLAB and want to calculate the DFT and IDFT of an expression, means if x of n is given, suppose x of n is 1, 2, 3, 4, right? Then the 4-point DFT of this will be, you can calculate it in simply in MATLAB by typing FFT x of n. This will give you the 4-point DFT of this, and this will give you x of k. That will be the x of k. And if you want to, if x of k is given, so if x of k is given, so this time this is given, and you are computing x of k. So you are computing x of k. Now in MATLAB, just type this FFT. This will give you the answer. Now, if x of k is now given, then what we do means our goal is to compute x of n back. What you will do, you will say I FFT means inverse fast Fourier transform. FFT stands for fast Fourier transform. We type this in small braces. In small braces, this will compute the IFT means x of n. This is how we do it. MATLAB, please remember this. This is very, very important. This is what actually is done. All right. Now, in the next session, we'll solve some examples based on this DFT, means discrete Fourier transformer idea. Please revise this. Have a look at these expressions. Please remember these two expressions. These are very, very important, and this is what actually computer uses to compute the Fourier transform expression. This is the expression. These are the expressions. These are also referred as discrete Fourier series. Also, they are same expression. This is not actually referred as discrete Fourier series, but the expressions are exactly same as that you have in discrete Fourier series. The expressions are same. The expressions are identical. So this is the discrete Fourier series expression. Also, this is the inverse discrete Fourier series expression. All right. Now this is not referred as discrete Fourier series. The expressions are identical, and this is the Fourier analysis that is actually evaluated by computer to evaluate the other three. Now, what do I mean by to evaluate the other three? Means to evaluate this Fourier series, Fourier transform, or discrete time Fourier transform. MATLAB, computer uses only this discrete time Fourier series actually. Discrete time Fourier series actually. All right. I hope you have got the idea. So this is very, very, very important. That's what computer actually uses to store or to evaluate the other transformers as well, but to Fourier transformers, be it Fourier series, Fourier transform, or discrete time Fourier transform, or discrete time Fourier series also. All right. All right. So this is DFT. This is IDFT. In the next session, we'll solve some examples based on this DFT.